Speaker is Tijs Karman from ITAMP, and he's going to tell us about conditional loss of ultracold molecules and how to prevent it.
Yeah, thank you very much, Mr. Chairman, and the organizers for giving me the opportunity to speak here. A brief outline of this talk is that I'll start with a short introduction and then talk about the sticky molecule scenario. In the second part of this talk, I'll talk about an alternate loss mechanism for ultracold molecules, that is, excitation by the trapping laser. And in the third part, I'll talk about preventing these losses using microwaves, and I'll close with some conclusions. So we're all here because ultracold molecules are a very promising platform for applications in quantum computing, simulation of quantum many-body systems, and to study novel quantum phases of matter. However, all of these applications require these samples at high densities, at which we expect fast collisional losses to occur. So molecule-molecule collisions lead to loss, and this can limit the coherence time of these molecules and the densities that we can achieve. So what do I mean by collisional loss? So for the original ultracold molecule, KRb, collisional loss could be reactions in two-body collisions. And this can be modeled theoretically by something called the universal loss model, which is basically assuming that molecules that approach each other into short range are lost with unit probability. And this accurately reproduces experimental loss rates for these molecules. To circumvent these losses, people then realized gases of non-reactive bialkalis, such as sodium rubidium, but also rubidium cesium, sodium potassium. And these gases, surprisingly, have much the same lifetime of in the order of a second or so. And in fact, there is now also evidence to suggest that indeed these molecules are also lost in two-body collisions with essentially unit probability. So this is shown here, for example, in this figure from a paper of the Dage and Wang group. So the markers are experimental loss rates or rate coefficients for loss of sodium rubidium molecules. And this is reproduced by this solid line, which is a coupled channels calculation by Goulf and Kemener. And this calculation assumes this unit probability loss at short range. And clearly that captures some of the loss. But again, these molecules are supposed to be chemically stable. And so it's not clear what this loss corresponds to. And to justify this unit probability loss at short range, people typically talk about sticky collisions. And so this is an idea that's been put forward by the John Bone group. And the basic idea is that for these collision complexes, whether that's molecule-atom or molecule-molecule, there is a very high density of states that basically results from, well, a density of states per channel and then a huge number of row vibrational channels contributing to quasi-bound states at near zero energy. So this, basically the idea is that during a collision, these molecules would chaotically, ergodically explore this large density of states, and that would lead to a sticking time that basically increases with that density of states. And again, because that could be very high, this could lead to a very long sticking time. And the idea is that might be long enough for a collision with a third molecule to occur, and that could be lossy. So something to note here is that this density of states, the relevant density of states is not the total density of states, but rather let me say this differently. In a collision, there are some conserved quantities, such as total angular momentum, and so the relevant density of states should be that the density of states restricted to that total angular momentum, and so we should count these row vibrational levels in a coupled representation. So we can count states, for example, like this. And it's worth noting that in these original papers by the Bone group, this is not what they did. They counted uncoupled channels that have some non-zero overlap, some non-zero Clebsch-Gordan coefficient with a particular total angular momentum. And this leads to an overestimate of the density of states by a factor 2n+1, where n is a rotational quantum number. And because rotational states up to the low hundreds contribute to the density of states, that leads to an overestimate by 2 or 3 orders of magnitude. So this is not new. This has been noted, for example, in this paper by Croft, Balakrishnan, and Kendrick. The second thing I'd like to note is that determining a density of states simply by counting these rho vibrational levels implies a certain uncoupling between these degrees of freedom and the radial degree of freedom. And so, strictly speaking, this doesn't apply to realistic potentials that depend on the orientations of the molecules and their vibrational coordinates. So to go beyond this, we've developed a semi-classical or a quasi-classical approach to calculating the density of states. And so the basic idea is that you can determine the density of states by a phase space integral of a delta function in energy. And it's not quite as simple as that, because again, we need to enforce certain conservation laws, such as that for total angular momentum, and that complicates these integrals a little bit. But still, you can integrate out momenta analytically, and it gives you a relatively simple expression for the density of states. So it's just an integral of some function that depends on the potential over the internal coordinates of the complex. And so this is a classical approximation, but that should be accurate for systems with high densities of states, and that's exactly what we're interested in. And again, this sort of phase space approach that would be valid for chaotic ergodic systems. Okay, so this is applying that to atom-molecule systems. So this is K+KRb, and we're looking at the density of states as a function of the energy relative to dissociation. And this is for a simple model potential, that is a Lennard-Jones potential that doesn't depend on the orientation of the molecule or its vibrational coordinate. And in that case, you can just count the density of states quantum mechanically, and that's shown by these markers. And this is accurately reproduced by our quasi-classical calculation, which is the solid line. Then we can also apply this to a molecule-molecule system. So this is sodium-potassium dimer. Again, we're looking at the density of states as a function of energy relative to dissociation. And so again, the quasi-classical calculation accurately reproduces the quantum result. That is, again, for a model Lennard-Jones potential. If we do this for an accurate ab initio potential, which does depend on the orientation of the molecule and vibrational coordinates, but otherwise it has the same well depth and the same C6, we obtain this result. So we obtain a significantly lower density of states. Then we've taken these results and derived sort of scaling laws with atomic masses and vibrational frequencies and C6 coefficients to extrapolate these results to the other bialkalis. So that's shown here. These numbers are the density of states in per microkelvin, and in parentheses we have the sticking times in microseconds. So you can see that there's a very steep scaling with the mass. And so the sticking times are longest for rubidium cesium molecules, and are around 500 microseconds. And it's worth noting that this is 2 orders of magnitude below the previous estimate of 45 milliseconds. So then the question is, what does that mean for loss? And again, the loss mechanism would be sticking until a collision with a third molecule occurs. And so to provide an estimate of that, we also estimate rate coefficients for these collisions, so collisions between the complex and the molecule. And this is estimated from C6 coefficients that we calculate from static polarizability. So these are known for the molecules, and again, we estimate or calculate quasi-classically for the collision complex. So this is a very rough order of magnitude estimate, because these numbers do depend on the particular system. But roughly the collision, the rate coefficients are in the order of 10 to the minus 10 cubic centimeter per second, whereas typical experimental densities are in the order of 10 to the 10 per cc. This gives a time between collisions in the order, very roughly in the order of a second, which is much longer than the sticking time, which again is 500 microseconds for rubidium cesium and much, much shorter for the lighter bialkalis. So because the sticking time, so the time that the complex lives for, is much shorter than the time between collisions, the complex likely dissociates before it undergoes three-body loss, and so this sticking amplified three-body loss, if that's what we want to call it, is inconsistent with the observed unit probability loss at short range. And if we do these estimates more quantitatively, then we see that for fermionic sodium-potassium, we should expect lifetimes in the order of an hour, and we obtain estimates of minutes to tens of minutes for the bosonic molecules. And both of these are, of course, much longer than the sort of second lifetimes observed experimentally. So again, sticking alone does not explain the loss that is observed. Okay, so then we consider a second loss mechanism, which would be the excitation of collision complexes by the trapping laser that is present in these experiments. So the idea is illustrated in this. This is a bit of a crowded plot, but this is again for sodium-potassium dimer for a symmetric orientation. So I fix the orientation of the molecules and look at the electronic energies as a function of the distance between them. And so we have a ground state potential here, and then a number of excited states. So the lowest threshold is here. This corresponds to a singlet sigma excitation of either of the molecules. And this correlates basically to the S to P transition along the molecular axis. Just above that, there is a threshold. This is a singlet state of the complex, but it has the two molecules excited to the triplet state. And yet above that, we have further thresholds that correspond to sort of the remaining components of S to P transitions of the atoms, and also different combinations of triplet states. This dashed line is the ground state potential that has been shifted vertically by the energy of a 1064 nanometer photon. So you can see that for the free molecules, so at large distance, this is red detuned from the lowest transition. But in the collision complex, these excited states are stabilized, and this shifted potential crosses various excited states before the ground state potential becomes repulsive. And so these electronic excitations are energetically they can occur. And again, because these correspond to sort of S to P transitions of the atoms, there should also be appreciable dipole moments. So this is a closer look at the dipole moment. So this is same system, same symmetric orientation, and we're looking at two states that have a symmetry-allowed dipole moment. The lowest one shown as the solid red line that asymptotically corresponds to a S to P transition, and the dipole moment that we see here is consistent with that. And the second state shown as a dashed line, that's this state where two molecules are excited to a triplet state, and so this has no allowed dipole moment. At finite distance, we see that these electronic states mix strongly, and so for the dipole moment, that means that the dipole for one state may decrease, the other may increase, but the total remains approximately constant. And at much shorter range, we see that the dipole moment is typically suppressed. And again, this is just a cut for a symmetric orientation, but we observe this sort of general behavior for global dipole surfaces. So I've now said that we actually calculate global dipole surfaces. We do the same for the potential energy surfaces, and then we want to use these to estimate the excitation rates. So we have a very, very simple model. So we basically have a rate equation which has an Einstein B coefficient. And the Einstein B coefficient essentially comes from, this phase space integral, which is an average over an average of the square dipole moment over the sort of local density of states. So this is, again, still assuming this ergodic dynamics where we can basically do an average over the entire accessible phase space. Okay, so these are the excitation rates that we obtain. So this is still for sodium potassium. This is at an experimental intensity of 30 kilowatts per square centimeter. And this figure is showing the excitation rate per microsecond as a function of the frequency of the trap laser. So the colored lines are the contributions of individual excited states, and towards the blue there would be excited states that we haven't included. The black line is the total excitation rate, and the vertical lines mark typical laser wavelengths. So at 1064 we see that the excitation rate is above 10 per microsecond, and it is much shorter, but at 1550, but it's still a few per microsecond, which is fast compared to sort of the lifetime of this collision complex, which is 36 microseconds for fermionic sodium potassium. So this means that any collision complex formed is likely likely excited by the laser and then presumably decays back to not the initial state. So it appears that this mechanism is consistent with this observed unit probability loss at short range. We can also look at this as a function of the trap intensity. So the red lines show the resulting lifetimes for the sodium-potassium molecules for 1064 and 1550 nanometer light. At low intensity, we see that the lifetime is limited by this three-body loss that I spoke about before. So this gives a lifetime in the order of hours. And if we increase the intensity, then the lifetime drops dramatically. And at some point, it saturates, where the lifetime is no longer limited by the excitation rate, but rather by the formation of these complexes in the first place. The vertical line marks a typical experimental intensity, which you can see is well into this saturated regime. And so again, complexes formed are essentially lost with unit probability, and this is in this regime roughly independent of the precise laser intensity and frequency. So I say this is a typical intensity, but in fact, if we look through the literature, there's quite some variation in this. So it may be possible to reduce this by almost 2 orders of magnitude, which would put us sort of at the point where it starts to saturate. So from that, it might be possible to observe some improvement in the lifetime by further reducing the intensity by switching to longer wavelengths. So I've said the first two things. So this is consistent with unit probability loss. We may observe some improvement by reducing intensity and going to longer wavelengths. But to really suppress losses, we need to do one of two things. The first would be to change the trap such that we essentially eliminate this laser. So that could be done by switching to, for example, magnetic trapping. Or if that's not possible for your molecule, then it may be possible to realize uniform box potential. So these have been realized for atoms, and basically the idea is that you use blue detuned light to construct sort of repulsive walls, and your molecules would be confined in between them and essentially reside in the dark. An alternate approach to suppressing the loss would be to not change the trap, but rather to suppress collisions between molecules. And so that would suppress the formation of these collision complexes in the first place. So the last part of this talk is about how we might do that using microwaves. And this slide illustrates the basic idea. So this is a schematic of the interaction potential for two ground state molecules. So it's basically attractive R⁻⁶ potential. And the idea is to apply microwaves that are blue detuned from the first rotational transition. And so that would give us an additional threshold which is split by resonant dipole-dipole interactions. And so this has a repulsive branch that at some point crosses the initial potential. And the idea would then be to increase the microwave intensity such that this crossing becomes avoided. And hopefully the molecules will adiabatically follow this upper potential and so collide without reaching short range, and they would be shielded. What might also happen is that the molecules actually traverse the crossing diabatically, in which case they reach short range, which is called RSR here. And this is precisely what we're trying to prevent from happening. A third process is that the molecules again make a non-adiabatic transition, but then they wind up in these lower thresholds, and so they dissociate with excess energy, and so this is microwave. We call this microwave-induced loss. The way we study this is by rigorous coupled channels calculations, where at long range we have the usual S-matrix boundary conditions, and then at short range we have a reactive capture boundary condition that models this unit probability loss. Okay, so these are some results for bosonic rubidium-cesium molecules, initially excluding hyperfine interactions. On the left we have the loss due to reaching short range, and on the right we have the microwave-induced loss. These are shown as a function of the Rabi frequency on the horizontal axis, so essentially the microwave intensity, and on the vertical axis we have the blue detuning. So you can see that in the lower right-hand sides of these figures, the losses due to both of these mechanisms can be made small, and so effective shielding is achievable. And in fact, we see that losses could be suppressed to below something like 10 to the minus 14 cubic centimeter per second. So this is 3 to 4 orders of magnitude below universal loss, and it would give us lifetimes of several seconds at densities high enough to load an optical lattice. This would require high but not unachievable Rabi frequencies of about 10 megahertz, and it would require circularly polarized microwaves. If we try the same thing for linear polarization, then basically, it won't work. Then the big question is, does it also work if we have a real molecule with complicated hyperfine interactions? So we study this, for example, for rubidium-cesium, where we're considering shielding of this spin-stretched state in blue, which could be prepared in the experiment, or typically is. So on the left we have the loss rates in the hyperfine free case, so this is what I've just shown you. On the right we have loss including hyperfine but at zero magnetic field. In the top, we see that the probability of reaching short range is essentially unaffected by hyperfine interactions. But unfortunately, the microwave-induced loss is not. So in the lower right-hand side of this figure, where you would achieve shielding, you see that the loss is enhanced by almost 2 orders of magnitude. But that is at zero magnetic field. If we look at the magnetic field dependence, then we see that indeed at low magnetic, this is for fixed Rabi frequency and detuning, and then we see that at low magnetic field, indeed, the loss is enhanced by 2 orders of magnitude, but this can easily be suppressed by applying a very modest magnetic field of only about 100 Gauss or so, and we basically recover the loss observed in the hyperfine free case. And again, the probability of reaching short range is much smaller and also essentially independent of hyperfine interactions. Okay, so this brings me to my conclusions. In the first part, I've shown that the density of states and sticking times were previously overestimated, and in fact, these cannot explain the loss of non-reactive ultracold molecules observed experimentally. In the second part, I've suggested a different loss mechanism, which is excitation of these collision complexes by the laser, and this is consistent with unit probability loss at short range. It may be possible to reduce this loss by significantly lowering the intensity and increasing the wavelength of the trapping laser. And further suppression would require either a different trapping where you can eliminate eliminate this trapping laser, or by shielding molecular collisions. And so in the last part, I've shown how that's possible using microwaves. And so achieving good shielding would, again, require circularly polarized microwaves of high intensities and a modest magnetic field to suppress the effect of hyperfine interactions. Finally, I'd like to thank my collaborators, so Arthur Christiane and Gerrit Groeneboom in Nijmegen, Martin Zwierlein at MIT, and Jeremy Hudson in Durham. And I'd like to acknowledge discussions with John Bone and James Croft regarding the discrepancy in the density of states. Thank you very much for your attention.
Questions? In the first part of your talk, you come to the conclusion with a model that you assume complete randomness, right, or ergodicity.
Yeah.
If you, I mean, is that possible? I mean, so that you have sort of an underlying assumption there that might or may not be true, right?
Yeah, that's right. But so, I think so there's the assumption of ergodicity in all of that. But I think in the first part, yeah, if you would assume that it's not ergodic, then it would probably stick less long, not longer.
It goes the other way, right? So, I mean, you wouldn't, I mean, what about if you have a resonance there's a longer way?
Yeah, I mean, then anything could happen, I guess. But, well, I mean, I don't know if you could actually have a single resonance that you happen to hit all the time, because the spacing, it should be narrower than sort of the spacing between levels. So, you know, if the density of states is high, then there should also be, if there are resonances, if you want to talk about it that way, then there should be many in sort of the thermal window of energies that you probe. So,
yeah, I think I agree with you. For the density of state calculation you have there, and you could, I mean, in principle, you can actually integrate the phase space directly, right? With quadrature. Is that what you did?
Yeah, that's essentially what we do. So, yeah.
But you said something that like momentum is down analytically. Is that necessary, or is it, you know, if you do the?
I mean, if you well, I mean, eliminating a bunch. I mean, it's high dimensional anyway, so right. Eliminating a bunch of these integrals analytically is.
So it's better. Okay.
I mean, yeah, if you can do it analytically, then it makes the calculation a bit simpler. But yeah.
But that's the assumption you have to have the two-dimensional potential, right?
Yeah, yes, you do. I mean, you can still do these sorts of things where you basically just have a simple Lennard-Jones, and it may be a useful estimate of the density of states. But this can also be applied for anisotropic potentials. Yeah.
So in the sodium rubidium work out of Deja-Walling's group,
yeah,
they observed a temperature dependence of the reaction rate. But in your model, it seems like there really shouldn't be much of a temperature dependence there. Is that correct, or is there something I'm missing?
So the temperature dependence. So again, this is a figure from Dejan Wang's group. So their observations are explained by this theory that has unit probability loss at short range, and then they fully include sort of the long range physics, and that part does have a temperature dependence. So we're just trying to understand what this unit probability loss at short range means. The temperature dependence itself would come from the long range part of the physics.
Long range physics would still be the same.
Yeah.
Okay.
Yeah.
I couldn't quite understand how generic this, trial excitation of the complex is. For example, if you turn it around and say what molecule wouldn't go away through this process. Have you thought about that?
Yeah, so one thing that we did look at is that our results. well, I don't know if I can find the slide, but one thing that we did look at is that what we have for sodium potassium is sort of independent of the precise dipole moment surface. We can basically use a simple model as S to P transition moment independent of geometry. That sort of works. The potentials, of course, do matter. I mean, if your excited states are not stabilized to below wherever your laser sits, then the loss would be 0.
Right, but the question is how much does that vary when you have such a complicated four-body system in terms of...
Yeah, so I think sort of the depth of that should be at least qualitatively similar between the bialkalis.
If you go to a high drive, for example.
Yeah, then it might be different. Yeah. Yeah, no, that would definitely be
I
different.
think first of all, it has to be polar, right? If it's not polar, if it's identical atoms, then you won't have this. Right? You require it as a permanent dipole moment.
No. It's an electronic transition dipole moment. So it's S to P transit for the alkali atoms. It would be sort of S to P like transition. So it would also happen if you have like K2 plus. Yeah.
So microwave should be what is for the curve that is physics, and then you apply for the ultracold, what about the dipole?
Yeah. So the dipole interaction is well basically all we include here really. So the C6 for a molecule like rubidium cesium comes from dipole interactions in second order. So the rotational part, not electronic. Or there is an electronic contribution, but it's relatively small for these systems. That's not the case for all. For KRb, that would be significant. And then what gives you the repulsion here is resonant dipole-dipole interactions also. So this would not work for a nonpolar molecule, the shielding. Yeah.
Yeah, so I thought I understood the counting of the density of the states, but you convinced me that I didn't. It makes me wonder what would happen just in an atom-molecule collision, where I now don't think I understand how much smaller the density of states there is, and therefore how much shorter the sticking time would be. But the same sort of excited complexes would exist there in not much lower density. So have you thought about atom-molecule collisions in light fields?
Yeah, so the density of states would be significantly lower for that, and I guess the excitation rates would be at best as high, but maybe lower. So probably laser excitation would not work in that case. If you just look at what we...
Many orders of magnitude into the saturated regime, so...
Yeah, so I mean just the difference in density of states. So this is for K+KRb, we have something like 20 or so, 20 per Kelvin, and here we have 10 to the 6 per Kelvin for the molecule. So there are many orders of magnitude between that. And for the molecule case, the excitation rate for sort of current experimental settings would be a few, maybe 2 orders of magnitude faster than dissociation. So for atom molecules, it should be slower. Yeah.
I think there is quite a bit of data on the different variation. I guess if I remember correctly, the rubidium cesium in German, they're using 1550 and 1064, so they're different wavelength time.
Yeah.
And how is your model going to apply when you now already have
Yeah, that would.
the data would be very interesting.
Yeah, that would be interesting to compare to. Yeah. Yeah, I mean, I've seen some curves of sort of the loss as a function of intensity, but you need a close look because there's also just the effect that changing the intensity changes the depth, changes the temperature, and that might be what's changing the loss.
Those numbers are all calibrated in some sense.
Yeah. Okay.
Yes.
In the table you gave for the sticking time for
Yeah.
density states, was that just rotationally excited states or was that vibrationally?
That's not including hyperfine, but it is including vibrations and rotations. Yeah.
But the hyperfine could maybe change that number by a significant factor? Not by 3 orders of magnitude.
Well, okay, so there is the question, if you believe, as I presented here, the dynamics is completely ergodic, then there's the question, is it also going to be ergodic in the hyperfine degree of freedom? If it is, then it's going to increase this by many orders of magnitude. The factor would be higher than just the number of hyperfine states. But yeah, we don't know whether that's ergodic. Yeah.
Yeah, in principle, you would be the hyperfine sublevels to the number of particles power, right? It's like 2f plus 1 and then to the n particle. I think we need to move on. Yeah, thanks the speaker again.